I spent 3 months designing and 3D printing this drone from scratch. Today, we find out whether it becomes a flying machine or just expensive spaghetti. It all began on a chilly December evening. I had just finished a project and I was restless. Suddenly, I had the bright idea of making something that could fly, which was a drone. So I went on the internet and did some research. After finding some good inspiration, I started to create my own design. I used my favorite CAD software, Autodesk Inventor, to model it all out. I made sure to conform to the specifications of the parts I was using. I used a traditional quadcopter design with curved arms and a place to contain the flight controller. After decreasing the size of the drone from over 100mm to just 75mm and adding all the necessary parts, I was ready to print. The 10-year-old printer took some frustrating hours of adjusting to make it work, but in the end, it was able to print my design. It was pretty clear the flight controller was not fitting, but at least the motors fit. Kinda. I realized I was completely clueless in the art of drone making, so I decided to change my design. A little bit. Yeah, it wasn't much better. Nevertheless, I decided to actually print my ill-conceived piece of plastic. After taking some screws from an old drone I had, I realized the motors fit on barely. I had to screw straight through the plastic. Once again, I had to change the design just a bit and print. Now the screws fit better, but the flight controller did not. So it was time to make some large-scale changes. After chamfering some of the holes, I began to add a support structure for the flight controller. In order to do this, I had to make the base larger. After modeling the supports and making a perfect replica of the flight controller inside the CAD, I realized I had more work to do. It was time to add color. After turning the project into an assembly, I carefully picked out the proper colors for the design. Then I began to work on modeling the motors for the drone using the proper dimensions, which involved many steps. And after completing those models, I had to model out the propeller. The propeller turned out to be one of the most challenging parts to model. I had never modeled a part with so many curves before. After many failed attempts, I found a YouTube video to help with the process. Using many work planes and a law feature which connects sketches together, I was able to finally make a propeller. It did not quite resemble the ones I was using in real life, but it was good enough. I also measured out the battery and quickly modeled it out as it was just a rectangular box. Now, it was time to make the parts fit together. First, I lowered the height of the flight controller so that the propellers could actually spin. Then, I created a platform for the battery to rest on. I would change this later, as the propellers were too close. Also, I created an opening on the bottom of the frame to put electronics and wires through. Next, I placed the rest of the motors and propellers on the frame. After placing constraints on the motors, I also fixed the opening for the electronics by modeling the connectors on the flight controller. I remodeled the opening around the connectors so I would be able to fit the board in. I added a little more color and then realized I had many issues with my CAD design. It all started with a simple chamfer. I was trying to make the motor holes larger to account for the 3D printing tolerance, but after I tried to constrain the motor, an error appeared. After a couple more tries, I realized I had deeper issues with my design. I looked through the errors and found out that the parts with the adaptive links were causing most of the errors. So I tried deleting all the related sketches, but that led to my parts disappearing. Then I tried deleting the chamfers, but when I added them back, the same errors kept appearing. Then I looked into the sketches and they weren't even constrained. So I realized my problem was with the reference geometry and I recreated the sketches without so many references. I rechamfered the base again, but once again, the errors appeared. Then, I redid the same sketch again, and all the other ones too. Finally, I reconstrained the motor and there were no more errors. I finished by adding legs to the drone. I decided to further increase the size of the drone to 105mm to make space for the propellers. However, after this, the software crashed every time I tried opening the project. At this point, I just wanted to throw my computer out the window. So, I just deleted all the reference geometry. And... oh my god. Well, I wouldn't give up so easily. I was going to redo every part if that's what it took. First, the flight controller. Once again, a crash. Then, the battery. There were still more errors. I redid the motor one final time. Now, for the moment of truth. And it worked. There were no more errors. It felt good to look at my error-free design, but it was time to move on. I added an opening to the top of the drone. Now, it was time to add screws to the model. I used a website called sigmamusicart to get models. Then, I attached the screws and nuts to their respective holes. With the finished design, it was time to print again. After completing the print and taking off the supports, I realized the holes weren't big enough to fit the screws for the flight controller, so I ended up having to screw them through. Then, I attached the flight controller to the frame, and I realized that the motor wires did not reach the flight controller. So, I set the frame back to 85mm in size. Because of this, the propellers are now too near the battery. So, I moved the battery underneath the drone. I added a little structure so I could use rubber bands to attach the battery, and so wires could go through it. After checking the length from the motor to the connector, it was time to print again. Taking the design out, removing the supports, and drilling small holes, I thought the design was going to be successful. The battery attachment worked, but I felt that the top was too flat and the motors were too close to the flight controller. I ended up rounding the edges of the frame and opened the bottom for easier wire access. Also, I added curved ascending arms to lift the motors and propeller, so they are not close to the flight controller. This was the most complicated part of the frame, but luckily, a certain Polish guy helped out. After completing that, it was time to print again. I went through all the steps only to realize the motor holes were off by a few millimeters. So, one more little change then. Then, repeating all the printing steps, I was finally able to install all the devices. With the base design now completed, I loaded up Betaflight to control the drone. It was a bit complicated to work with at first, but soon I had the transmitter and flight controller all connected up. It also took a couple of tries to wire up the motors correctly, but after lining up the motors, the drone was able to fly. However, it was near impossible to control properly. The drone landed on concrete, and yeah, there wasn't much left of it after. I reprinted the drone and then applied some throttle PID tuning. This way, the drone would accelerate gradually and not jump all over the place. Unfortunately, I was terrible at flying drones, and it was smashed again. So, I applied some finite element analysis to figure out the most vulnerable parts of the drone. Of course, it was the arm. So, I made the arms and legs a bit thicker and sturdy and then reprinted the design, but then it broke. So, I made the arms even more thicker, added landing gear similar to a helicopter since there's a reason they have it, and added 2 more arms to distribute the force. With my old printer now completely broken, I moved on to a new printer which could now print carbon fiber composite. It worked so well, I actually had to do very little modifications. With all that, the drone became much more strong and more manageable to control. One could say I was done, but I felt there was something missing. Before moving on, I want to explain what I built. I'm using the Matrix 5-in-1 brushless flight controller. Looking closer, you can see the 5.8 GHz VTX chip which transmits video, the receiver and receiver antenna which receives commands from a radio transmitter, the VTX antenna, the battery connector, and the camera input. Looking back out, you can see the 4 brushless motors powering the flight of the drone. Each motor is 19,500 kV and 1S, allowing for a fast and efficient throttle response with a single 3.7 volt LiPo battery. The propellers are 40mm wide and 2-blade, with a 1mm hole to fit onto the motors, making them very efficient. Moving on to the frame, it is made from top-of-the-line PA12 carbon fiber nylon filament, making it lightweight and extremely durable at 85mm in size. On the other side of the drone, you can see the STM32G473 microcontroller which runs Betaflight and Sense commands. It contains an ARM Cortex M4 processor running up to 170 MHz, which is fast for running control loops. There's also the on-screen display chip, which adds an information overlay on the analog video feed. Next, there's the Express LRS SPI receiver, which allows long-range and low-latency communication with the drone using the ELRS system. Additionally, there are 4 electronic speed controllers and their respective connectors, which control the switching of the current in the coils of the brushless motors to make them spin. Finally, there's the camera pins, the FCRX boot which puts the flight controller into boot mode, a Beta FPV BT 2.0 connector, replacing a PH 2.0 connector, and the USB connector. To power the drone, I'm using a 300 mAh 1S 3.8 volt LiPo battery, held by rubber bands. For my transmitter, I'm using the cheapest one I could get, which was this Beta FPV Light Radio 2 ELRS V3 transmitter. After binding the drone and arming arming the motors, I was able to control the drone. Now, it was time to add a FPV camera. I used a Beta FPV C03 FPV camera, and at this point I was basically just recreating a Beta FPV drone. But no matter, I recreated the camera in CAD, created a holder for it, and fit it together in the assembly. I printed out the holder, which fit perfectly. Then I printed out the drone top with a minor change to better fit the flight controller. Now, it was time to put it all together and complete the design. After screwing the camera to the drone top, and then attaching it to the drone, it was ready to fly. Unfortunately, I had problems with the motor, which resulted in me taking it apart to remove friction. Now that it could finally fly, and I could see through the camera with my receiver, I realized it was now too heavy to fly up. So, I ended up weighing the drone with the camera setup and without, and there was about a 10-gram difference. I investigated further, and it turned out the camera top weighed nothing. The drone could fly fine with it being taped, but 4 M3 steel screws were surprisingly heavy. So I switched to nylon screws, which were a lot less heavy, and now the drone was able to fly just fine. I absolutely enjoyed seeing my design somehow managing to work, but I felt that I hadn't quite reached the limits of it yet. So I decided to try making the drone fly autonomously. Here's how it would work. Normally, the drone can't take commands from a computer by itself. However, you could use a transmitter module to send commands. The computer pretends to be a stick controller by streaming CRSF commands, which is a serial protocol, over the ELRS radio link. The flight controller then reads those values as it runs beta flight. This way, the drone would require very little modification since the commands are directly taken in without needing an external microcontroller. Now, by switching DIP1 and 2 on the back of the transmitter to on to trick it into firmware upgrade mode, which opens a direct communication channel with the computer. You can now build and flash ELRS with a proper binding phase to the receiver and transmitter, and then by disabling interfering backpack pin communication, you can have full control of the drone with Python. Of course, I used a little AI to connect the devices together, and now I had the computer synced up to the drone. After testing some scripts to arm the drone properly, it was time to make it fly by itself. After an initial thrust test, I was trying to get the drone to hover properly. However, I did not have a GPS for measuring distance or a barometer for measuring height on the drone, so I had to try fine-tuning the parameters for hovering and correcting for drift manually. There were a few accidents in the process, but I was slowly but surely making progress. Soon, I even had the drone flying and going forward, but then not even carbon fiber can prevent damage from such a crash, and I realized that I had reached the limits of my drone design. However, this might not be the end just yet, and I hope to be able to make a bigger and better drone that's actually able to fly by itself. Here's the final setup I had trying to make everything work in my basement. And here's the evolution of the drone design. This journey is not over yet, but for now, thank you for watching.